So I need to record this kind of quick because I noticed that they did not give me the full video from the recording studio. So in the meantime, we will do it this way. What I have here, I have to think about what is that substance. And I go through my list of ideas, and I know that this is a weak base. Now let me tell you why I know that. I look for this nitrogen here, and when I see it, and I have a nitrogen with three things connected, three bonds to it, okay? So I have two hydrogens, and I have this group here that you see written there as the third bond. I know that I am dealing with a base. That is a telltale sign, nitrogen with three bonds connected to it. Because there's a lone pair always on that nitrogen, and it is ready to accept a proton. Now I know this is certainly not on my strong base list, which are all metal hydroxides, so I know I'm dealing with a weak base. And I will proceed to write that weak base reaction. C2H5NH2 is going to be placed into water. And as I do that, I know it will do the base thing, which is to be a proton acceptor. Who does it accept it from? It accepts it from water. Where does it go? Well, it attaches to the nitrogen. So instead of NH2, I'll have NH3. I know it is an H plus that it is accepting, so it'll make the charge go up by 1. And what will we have with water? Well, water, since it donated, has one less hydrogen, one less H plus, which gives me the OH minus, and that is a base. Now, you can write all that out. I very often will just let a B represent my base because it will always do the same thing. What will it do? It will accept a proton and become the cation, and the water will become OH minus. So you will sometimes see me write it this way just because it always gives me that same reaction. I'm going to leave room for an ICE table underneath that. But I'm not going to just blindly fill in a bunch of information and start putting X's in, which is what I see a lot of students do. I make sure I fill in everything I can and see if I can not have to do an X. I know that the original concentration is 1.2. I know I don't have to do anything with water, and I have a 0 here and a 0 here. And I look and see what other information is given to me. I am given a pH. It's 12.41. I know with that pH, I could eventually get the OH minus concentration that goes right there. So let's get that value. If the pH is equal to 12.41, then the pOH is equal to 14 minus that 12.41. And so the pOH is 1.59. Then to get the OH minus concentration, I'm going to take 10 to the minus 1.59, and that will give me an OH concentration equal to 0.0257. And that can go in here. Now, as soon as I have an initial and a final amount underneath the OH minus, I can fill in my table. I know I had to have produced 0.0257. And if I produced it there, I'm also going to produce it here for the conjugate acid. And I'm going to consume it here. When I subtract those values, I am going to have 1.17. Now, truly, to only one place past the decimal point, it is still 1.2, but I'm going to carry the extra sig figs as I work through the problem and then eliminate them at the end. So the next thing I need to do is write my KB expression because that's what I'm trying to determine. I know it's BH plus concentration times OH minus concentration divided by B's concentration. So then I can plug those values in. I have 0.0257 for this number, and the same for the OH minus, so I can square it, divided by 1.17. And when I plug all of those values in, I end up with a value of 5.6 times 10 to the minus 4. And that is the value of KB. All right, let's look at our next problem here. Here we're going to do a very different problem. Again, they're giving me a pH, but this time they're giving me the KB, and they want to know what is the original molarity of the ammonia solution. Now, I know that ammonia is NH3, and I could write the reaction with NH3, and I will. Proton swap, the base accepts the proton, the water donates the proton, and there's the reaction. I could have done it with B's instead, and I'll do that right above it so you can see it. BH plus OH minus. That would be fine. And I have an ICE table. Now this time it's a little bit different because I want to know the original molarity of the ammonia. I want to know this. I don't know it, so I'm going to call it X. I know these are 0, and I look for what else they give me. They gave me a pH of 11.22. I want you to tell me what would go right here if I know the pH is 11.22. Well, did you get 0.00166? Well, that's correct, obviously. And how did you get that? Well, you would need to take the pH, obtain the pOH, and then from there you would get the OH minus concentration. So now we have a value that I can fill in the table with, 0.012, 00166, 00166, and minus. So over here under the E of NH3, we have this, our unknown. So let's write our KB expression. We know that KB is the NH4 concentration times the OH minus concentration divided by the NH3 concentration at equilibrium. Plugging in what I know, I've got a value of KB equal to 1.8 times 10 to the minus 5. I have 0.00166 squared on the top, and I have X minus 0.00166. So now I have my equation where I can solve for X. First thing I want to do is I want to multiply both sides by the denominator I see right there. So that's 1.8 times 10 to the minus 5 times X minus 0.00166. And that's going to be equal to what we see up here, the numerator. I'm going to go ahead and square that, and I have 2.75 times 10 to the minus 6. I will do the distributive property. This is 1.8 times 10 to the minus 5, X, minus, when I multiply those two values, I get 2.99 times 10 to the minus 8, and that is equal to 2.75 times 10 to the minus 6. I will add this to both sides. That will give me 1.8 times 10 to the minus 5x is equal to 2.78. I'm adding it, so it goes up a little bit, times 10 to the minus 6. Then I will divide by the 1.8 times 10 to the minus 5, and it leaves me with an x equal to 0.15. And since x was the original concentration of ammonia, I have found my answer. Okay, our next problem is this one. We're going to calculate the pH. Now I'm going to first ask you this question because this is a very important question to ask so that we know that we are on track when we get our answer. So will the pH be less than 7, equal to 7, or greater than 7? Well, it is going to be greater than 7, and I know this because I've established that this thing is a weak base. Now, you may have no understanding of what pyridine is, but you knew we were working in weak bases, so maybe you figured it was a weak base that way. But here's how I would know it's a weak base. Notice that they gave me a value of a Kb for it. Well, if they gave me a value of a Kb for it, it is a good giveaway that we're dealing with a base. So now let's go ahead and work the problem. Give myself a full page here to work it. I don't know the formula for pyridine, so in this case, I'm just going to call it a base. I place that base in water, and it will do the base thing. It will accept a proton. When it accepts that H+, it becomes BH+, and the water becomes OH-. I will set up my ICE table and plug anything in that I can find that's useful. They tell me the original concentration is 0.5, so I know these are 0. And that's all they give me that I can put in the table. They give me a Kb value, and that is equal to 3.8 times 10 to the minus 10, and I know the expression is BH plus times OH minus divided by B. But that's all I know. So here I have to use my variable. So I will consume some of the base. I will produce on this side, and that will give me 0.5 minus x, x, and x. And I can plug this into my expression. 3.8 times 10 to the minus 10 is equal to x times x divided by 0.5 minus x. Now here I'm going to assume, because look at that tiny k, I'm going to assume that x is much, much smaller than 0.50. That will allow me to ignore that term right there and make it a lot easier to solve for. So when I do that, I have 3.8 times 10 to the minus 10 times that 0.5. I'm bringing it over by multiplying it by both sides, and that is equal to x squared. And if I take the square root of both sides, I will be left with x. In this case, I have an x equal to 1.38 times 10 to the minus 5. Now let's check our assumption. Is that much, much smaller than 0.5? It certainly is. All right, now let's think about what x is. If we look up here, we see that x is the OH minus concentration. Of course, it's also the BH plus concentration, but what I'm trying to find is pH. If I'm trying to find pH, it is the fact that it is the OH minus concentration that I need to know. So let's take that x and first get the pOH by taking the negative log. This is going to give me a pOH value of 4.86. Now, a lot of students will sometimes just take the negative log of this blindly, not thinking about that. And if they got a value for this, they had to, the advantage of thinking about what should the pH be is here. If we have a 4.86 value and we think that's the answer, that is an acid's pH, and this is a base, so I know that can't be right. I was looking for something that was greater than 7. Well, since I know it's pOH, to get the pH, I have to take 14 minus 4.86. And that's going to give me my pH value of 9.14, and certainly that is a useful value for me in terms of it is greater than 7. So I like my answer, and I will accept that. Okay, so we've gone through a whole series of weak base problems. I've given you a variety of them, and now you can practice.